Okay.
Okay, so start this warm-up question. Yeah, it's recording. No, that won't have the clarity. So this is for you to access in case you want to revise the classes. See, the next concept is order of magnitude, which we haven't discussed, but you can guess intuitively. So physicists need to use their intuition to guess the answers very often, quickly. It's like if you're on the field and you want to estimate something, before you do the rigorous mathematical calculation which may give you the accurate result in decimal places and all that, you want to know whether your calculated answer is correct or not. You want to guide your intuition, right? So for that you just use order of magnitude calculations. So number of heartbeats of a person in 1 hour. So you want to calculate that. So what will you do? In a minute, how many heartbeats does a human have average?
100.
86. 80 or 70?
76 to
80. Okay, 76 to 80. So let us say 80 per minute. And we are asking in 1 hour, right?
So 4800.
So 80 into 60. Agreed? So this is supposed to be the answer. But suppose you don't want to waste your time calculating accurately, you can just take the nearest, round everything to the nearest 100. Or if it's easy to calculate, you can do that calculation and then round it to the nearest power of 10. So 4800 it becomes. So you can make it as 4.8 into 10 power 3. Now 4.8 is closer to 1 or closer to 10?
1.
So, but the way to find whether it is closer to 1 or closer to 10 is, we are doing it in powers of 10, remember? So, the next lower power than 10 is, you have to say root 10. You have to compare the value with root 10. What is root 10? Take a calculator, tell me what is root 10. It's 3 point something, no? How much exactly?
3.667.
3.667?
3.162.
So root 10 is 3.16. Okay? So if this number is less than 3.16, we'll round it off as 1. If it's more than 3.16, more than root 10, we'll round it off as 10. We'll say the order of magnitude is closer to 10. So in this case, we'll say it's closer to 10. So we'll say it's almost equal to 10 power 4. Is there any option which is nearest to that?
No.
So what will you do in an exam? Will you choose 10 per 5 or 10 per 3?
5. 3.
Because if you take it as closer to 1, then this will become 10 per 3. Agreed? So in the exam you may have such situations. These are all from past papers only. So we'll go with 10 per 3. Let's check the answer key. So all this has been shared with you, the resources folder.
Yes, sir.
So you go to this solutions, go to this intro to physics, order of magnitude and estimation 1C. What did we do?
3.
1C. You got it? So like this, you will have a lot of fun practicing these questions. The IB questions are all like puzzles, thinking based questions. Okay? Close your laptops please. You need to do the work in your notebook. Look at the board.
So this is quite vague.
No, when I want you to do a question, I will zoom it. Don't worry. So this was just to get you started with the warm-up question. Now, in the resources given to you, you also have this Oxford IB Physics course companion. Okay, so it's a very good, concise collection of notes. So order of magnitude, estimation is done. Then uncertainties and errors. So here you can see the new concepts, next new concepts you need to know. What is random and systematic error, absolute fractional percentage error, and uncertainty of gradient in intercepts. So these are the next few concepts which you are going to learn. So what is a quick way to make it black screen?
What?
There is some
Blank, this is blank. There's a button that says blank.
I don't see any line. Some quick view was there. What? We'll just open a notepad. Okay. So random and systematic errors. So yesterday we found out the difference between precision and accuracy, right?
Yeah.
In that, the way Arnav Sethi was shooting, he had a very poor precision, but by luck, his result turned out to be accurate. Agreed? So when the precision is very bad, that means your instrument gives readings which are all over the place. They have too much fluctuation. Okay? So that kind of error is called random error because you can't control that error. You can't even predict what is causing that deviation. And it's some random influence. For example, you drop a ball on the table and you want to measure the rebound height. So you take the same table tennis ball and drop it from the same height. Shiva, please. And drop it from the same height. Do you think that every time it will bounce the same height back? According to physics, it should, right? You drop it from the same height, so it has the same gravitational potential energy. So if you release it, it should bounce back to the same height.
Yeah.
Because every time it hits, it will lose some kinetic energy to the collision, and it will have less kinetic energy left, which will get converted back to gravitational potential energy, which will correspond to some height. So if you drop it in the same way every time, the rebound height should be the same every time. But if you actually make the measurement accurately, you will find that it drops from here, and then first time it came till here, second time it came till here, third time it came till here, fourth time it came till here, fifth time it came till here. So if you see, actually there is some slight variation each time. You see that? It varies, but more or less it lies within this range. So the rebound height, let us call it HR, varies within a certain range. So let us call it delta H. So this delta H is the uncertainty in the rebound height. And this uncertainty is due to a random error. Yes.
So the less the range, the more the precision.
Yes. Less the range in uncertainty, more the precision. So this delta H is called as absolute error. So absolute error refers to the actual uncertainty in the measured value. So each measurement you take, it will have some range within which it lies. Even if I measure it 1,000 times, I can say that it lies within this minimum and this maximum value. It doesn't fluctuate more than that. So that range you can get if you take 5 trials usually. So that's why we keep it as a standard and take 5 trials. If you take 5 trials, it's a good enough number that you don't, you will cover all possibilities, the maximum and minimum fluctuations. Clear? And then when you take 5 trials, if you take the mean of those, the mean value. So if it has one maximum, it has one minimum, and there is equal probability of reaching the maximum deviation and the minimum deviation, then they will cancel each other's effects and the mean will be close to the true value. Agreed? So if you make it bounce like 10,000 times, the mean will be more accurate compared to making it bounce only 2 times. Agreed? So that's why we increase the number of trials to make the mean approach the true value closer and closer. Okay? So our standard way of finding absolute error is max, please note this down, max minus min by 2 of all the trials. So you take a measurement 5 times.
Basically the range. So no.
Yeah. The range will be max minus min.
And then divide by 2.
And then when you divide it by 2, this becomes your delta H. So half of the range is basically half of the range.
So what exactly is the absolute error?
What exactly is the
Absolute error.
So absolute error tells you by how much the mean value can fluctuate. It gives you the confidence in your measurement. So if I say the rebound height is 3.3 plus or minus 0.3, that means the rebound height can be anything between 3.6 and 3.0. Not, it can't lie outside this range.
If it does, then it's a human error.
Yeah. Your measurement has this much answer. Yes. Yeah. Clear now? And never forget to write the unit for whatever you measure. So absolute error is clear. So suppose you are measuring the time interval between two consecutive bounces. So the ball is bouncing like this. So between this point to this point, you have delta t, you have t, okay? The time interval between first hitting the ground and then second time. So using a stopwatch you are measuring. So first time you may measure 2.1, next time 2.0, next time 2.2, next time 1.9, like that. So again you will find the max minus min by 2. So in Excel you will do all these calculations automatically using a formula. I will demonstrate. Should I demonstrate now itself?
No, not right now, sir.
No,
Just getting the
now first
concept
the
clear.
concepts.
Yeah.
Then when we do the IA that time, when we do the lab experiment, I will tell you how to use Excel.
Yes, sir.
So absolute error is done. Now this is not enough to give us a true picture of whether the measurement, whether the instrument we are using is appropriate or not. I'll tell you why. Suppose you want to measure the thickness of a wire. Let us say this is the wire.
Micrometers per wheel.
Okay. So I have meter scale. Which has a least count of 0.1 centimeter. Okay. And I am using it to measure the thickness of the wire and also the length of the wire. This is thickness, this is length. So let us say length is 100 centimeter. So we have measured it to an absolute error of plus or minus 0.1 centimeter. And let us say thickness is 0.1 centimeter. We have again measured it to an absolute error of plus or minus 0.1 centimeter.
I'm a bit confused. So even if you measure it to an absolute error,
That means the value lies
See,
between.
whatever is the least count of the instrument, that is the uncertainty in the measurement, right?
yeah.
So if I say that its value is 100 point, I should record it as 100.0 centimeter
Yeah.
plus or minus 0.1 centimeter. This will be recorded as 0.1 centimeter plus or minus 0.1 centimeter. So now, if you compare the absolute error, both have the same absolute error. So can you say that both measurements are equally good? The accuracy, the precision is equally good? Harry, what do you think? Can we say both these measurements are equally good?
Yeah.
So that's where the mistake is. By just comparing absolute error, you think the uncertainty is same in both, so they're equally good. Like that you might think. But actually, just think about it. This is 0.1 centimeter plus or minus 0.1 centimeter. It could be 0.1 centimeter, it could be 0 centimeter, it could be 0.2 centimeter. So, is that measurement of any use? It could be, look at the percentage uncertainty in it. It could be 0, it could be 0.1, it could be double its value, it could be nothing, it could be double its value. Whereas look at this one, it lies between 99.9
100.1.
and 100.1. So it's highly accurate, right? We know it's between these two values. Whereas this case, it's all over the place. It could be 0, it could be double the value, it could be. So a better way of coming to a conclusion about whether your instrument is appropriate for your measurement is relative error. So relative error is defined as, in this case it will be delta L by L, which means this is the absolute error and this is the true value or mean value. If you know the actual value, that you should write. So how do we know the actual value when we make a measurement? The mean value is the mean value refers to the actual or true value. So in this example, what is the relative error? Delta L by L would be 0. Okay, Harry, tell me, what is the absolute error in this measurement?
So it's delta R, right?
Yes. Like we know its measurement is 100.0 centimeter, but what is the range in which it can lie?
Plus or minus 0.1.
Yes, so this is the absolute error.
Yeah.
So this is the delta L.
Okay.
So 0.1 centimeter divided by, what is the actual true value of that length? 100.0 centimeter. So what is the relative error? 1 by 1000. So the uncertainty is only 1 in 1000 of your measured value. So which is pretty good. The confidence in your measurement is that the uncertainty is what fraction of the true value? 1 in 1000. So whatever you have measured, only 1 in 1000 uncertainty is there. Whereas in this case, Harry, again tell me, delta L by L, how much would it be in this case? What is the uncertainty in this?
0.1.
And what is the true value?
0.1 as well.
So now we will get it as 1. The entire measurement is uncertain. Are you getting it? So even more better way of comparing the relative uncertainty is percentage uncertainty. It is basically relative uncertainty into 100. Now here I have written L, it could be anything. If you are measuring height, it will be delta H by H, mass, delta M by M, time, delta T by T, any measured quantity. Shiva, please. Okay? So now what it does is, this gives you the percentage with respect to 100%. 100% meaning hopeless measurement. 0% means the percentage uncertainty is 0. It's like you got the true value itself. So now you can tell what is this. So if you do it with into 100, if you multiply, you get 0.1%. Agreed? Which is very accurate, very precise. Whereas in this case, you get 100%. Very hopeless.
So that means it's definitely an error.
Yeah, this instrument is not the appropriate instrument for this measurement. To measure a thickness of a wire which is just 0.1 centimeter, you should not use meter scale. You should use something better, which has a better, smaller least count. Say a screw gauge. Screw gauge will have 0.001 centimeter. So then in that case, look at the percentage uncertainty into 100. If you do, it will become 0.1. It will become how much? 1%. Yeah, 0.1 by 0.1 is 1%, which is acceptable. So if a wire is only 0.1 centimeter thick, you should use screw gauge. Then the percentage uncertainty will become 1%, which is okay. So in a typical experiment, anything less than 5% is acceptable. So always choose your instrument appropriately. So would you use a meter scale to measure distance or to measure the distance from here to the CDH? It won't be an appropriate instrument. Just because you want to measure accurately, you can't use a microscope to measure the length also, right? So you Use the optimum one. As long as you can get less than 5% error, it's fine. Don't go for 1 millionth percent, 10 per minus 5% error. It's a waste. It's not worth the effort. Clear? So we have covered the 3 types of errors. Random error also you understood. Now what is systematic error? So can I erase? So systematic error is an example of who was doing systematic error yesterday? Vedant. Who did systematic? Okay, what I mean is very precise but inaccurate. Vedant, right? So suppose all your readings, suppose the actual mass is 50.0 kg. This is a true value, let us say. And the person stands on the weighing machine and it always gives 60.0 kg. Now let us say Arnav's mass
100. I'm kidding. 80.
Okay, let's take a round here. And this instrument says 110 kg.
Break it.
Okay, suppose someone else says 70 kg. And this instrument says 80 kg. So would you get fed up and say, what a useless weighing machine, it gives always wrong answers, wrong measurements, and throw it off?
Yes.
You throw it away?
No, you recalibrate it.
Who said yes? If you throw this machine, you are wasting it. You are wasting the money.
You can recalibrate it.
No need to even recalibrate it.
अच्छा minus कर दो.
This is an error which is called systematic error. It's giving the same kind of error in every measurement, which if you are smart, if you can identify, you can cut it off, cancel it. How can you cancel it?
Minus 10.
Yeah. So the true value, so correction for systematic error. Please note this, correction for systematic error. Is true value minus measured value. So for example, in each of these cases, what will you get? This case, true value is 50.
So is it ulta? Isn't it measured value minus 50?
I said correction, not the error.
Okay.
So in this case it will be 50 minus 60, which is minus 10. So if you do this, so this is the correction. So whatever is the corrected value would be, corrected measured value would be measured value plus correction. So in this case, measured value was how much? 60. Plus the correction is minus 10, which is 50.0, which is the true value. So once you know that your instrument is giving a systematic error, and once you identify the error, you can find the correction and then incorporate that correction to all the measured values, you will get the corrected value. So now this systematic error could be a fault of the instrument. In that case, we call it as zero error. So zero error is a type of systematic error where the instrument is at fault. So for example, your screw gauge, when it is fully, when the gap is made zero, when the gap is made zero in a screw gauge, it is supposed to show zero division, right? But instead it shows plus 5 divisions. That means it is saying that there is a gap corresponding to 5 circular scale divisions, when actually there is zero gap. Then when there is actually 5 circular scale division, what will it show? How many divisions will it show? 10. So that means if it is showing extra 5 divisions, you have to subtract that extra 5 divisions from every measurement.
So, but when we do this, when we calculate the correction systematic error, we assume that the error would be an arithmetic error.
Yeah.
The multiplication ka error would then imagine if it's 40 is showing 80 and 30 is showing 60.
No, instrument won't work like that.
It
No?
won't work like that.
Yeah, a systematic error is always an arithmetic error because there is some shift in the zero position. So a weighing machine, the needle instead of showing 0, it is shifted to the left of 0.
Yeah.
Typically it happens, no, weighing machine, the needle keeps shifting. So if you stand on it, when it is supposed to show 10 kg, it may show 5 kg. When it is supposed to show 25 kg, it may show 20 kg.
It's 5
Like that.
inches.
So this kind of systematic error is very common in all the instruments, analog instruments, say voltmeter, ammeter, which has needles. So you have two options. One, identify the error and then make the correction after taking the measurements, or remove the zero error. So in all these voltmeters, ammeters, weighing machines, analog devices, you will have a screw by which you can turn the needle so that it's exactly at the zero position when it is supposed to be 0. Okay? Then once the zero error is eliminated, you have eliminated the systematic error. Otherwise, if you can't do that, just do it by calculation. Now there is also human systematic error.
Reaction time, I suggest.
Yeah. No, reaction time cannot be a systematic error.
Okay, it's random.
Because each time, sometimes you may click in advance, sometimes you may click later. So human reaction time is not a systematic error, it's a random error. You have a question?
So systematic errors and zero errors are the same thing, basically.
Yeah, zero error is a type of systematic error.
Then what are the different types of systematic or human?
Yeah, so the other one is human systematic error. So for example, you have this measuring cylinder. Okay, it has these divisions, and this is the water. So in water, the lower meniscus reading you are supposed to take, which means this reading. But suppose you did not realize that and you took this reading. So this is say 10 ml and this is 11 ml. So where it is supposed to say 10 ml, you have noted it as 11 ml because you noted the upper meniscus. Whereas below the inside the cylinder, you see it's all empty space. The liquid is only up to the lower meniscus. So that's a human error. It is not the instrument's fault. You read it wrong.
So it's parallax.
This is not a parallax error. This is a conceptually you did the measurement in the wrong method. You are supposed to note the lower meniscus for transparent liquids like water, but instead you measured the upper meniscus. So it gave you 1 ml extra error in everything. So you have to subtract 1 ml from all your readings if you identify this. So in IB, what happens is when you do your internal assessment, they have a section called analysis and evaluation. So when you plot your graph, so how do you know from your data whether you have systematic errors? Suppose you plot a graph, you expected a graph to pass through origin. Because y was proportional to x, you expected it to pass through origin. Instead, when you plot the graph of your data, you find that it is like this. This is a clear proof that there is a systematic error. Because every value of y is extra by some amount, by the same amount. So if this error had been subtracted from all the values, it would have passed through the origin. So when you have a y-intercept when it is not supposed to be there from your theoretical expectation, that's an indication that there is systematic error. You have to comment about that in your evaluation section, which will give you marks. So even though you made a mistake in your measurement, causing error in your data, you are not penalized for it, instead you are rewarded for it. Because you have identified the systematic error and you have commented about it. So that's what IB wants. IB wants you to make mistakes and then identify the mistakes and correct the mistakes. Okay? So the idea is you have to work independently, make mistakes and then learn from the mistakes and report about what all you learned from the mistakes. One more way of creating systematic error by the human systematic error method is like, if you measure, you kept the beaker on top of a stool and did the measurements. So it was not at eye level, it was above eye level. So from your eyesight, you will see like this. I need to draw it in an exaggerated manner. So you will note down this reading. Wait, then this one will be correct. Okay. Now let us say this is the level. Okay? This is supposed to be the true reading, but you end up reading this. Are you getting what I'm saying? You are seeing from below. So actual reading is supposed to be 11 ml, but instead you record it as 10 ml because you are seeing from below. If you see from this side, exactly at the level, then you will see that it's 11 ml. So this is an example of parallax error. So all the measurements you did the same kind of parallax error. So the systematic error is same type, so you can correct for it. Or if you see from above, again you will measure it as 12 ml. So the systematic error is of the other side. Understood now? Clear? So systematic error is done, random error is done, types of error is done. Okay, next is error propagation. Can you erase this? So once we finish error propagation, you are done with this chapter. So error propagation is basically when you make 2-3 measurements and use it to calculate some new quantity. What happened? So when you, for example, yesterday did you do volume using length, breadth, height? Okay. Let us say volume is length into breadth into height. This is one set of quantity. And let us say you have another quantity where you need to measure the total length of, you measure the length of 3 different rods. L1, L2, L3. So you want, if you join them, if you stack them together one after another, what would be the new length? So then you get L equals L1 plus L2 plus L3. Okay? And let us say you have a function y equals x per a, z per b, by p per c, r per d. This is some complicated function where a, b, c, d are numbers, x, y, p, r are measurements. Okay? So each of these measurements L, B, H, L1, L2, L3 has some absolute error. So L will have delta L, B will have delta B, H will have delta H. So delta represents a change, an uncertainty. Clear? So because of all these uncertainties, the calculated value will also have some uncertainty. Yes or no? Agreed? So we want to know how much would the uncertainty in the calculated value be, which we will call delta V. In this case it will be called delta L. In this case it will be called delta Y. Okay? So that is our goal. How does the error in the measured quantities propagate or transfer to the error in the calculated result? So when you finally report your result of your experiment, which you calculate from all the measured quantities, you should report it with the proper uncertainty. Okay? So for that there are two situations. One is plus or minus calculations. Another is multiplication or division calculations. Okay? Or even the power. Multiplication, division, power, they have a separate kind of treatment. Addition, subtraction has a separate kind of treatment. And you also have complicated functions. like sine, cosine, tan, then what? All other kinds of strain functions which you may not know what to do, which are different from these two anyways. So each of these have three different approaches to find the error in the result. So for this, you have to use absolute error. Make a note. For addition and subtraction, what will you do? Vedant? You have to sleep well at home at night so that you are fresh in the morning. For multiplication, division and power, what will you use? Relative error or percentage error. And for these you will use max minus min by 2. Actually this is common for everything. Max minus min by 2 method you can do for everything. I'll explain what each of these three methods are now one by one. Okay? So you want to know what is the uncertainty in the final result. Understood the task before us? Okay. Oh. Class is over, so we'll continue next class, these three things. Just stop the video.